Hello. Okay. Hello, everyone. What we're going to be doing today, um, since there was since we had to miss a couple classes this semester, we're going to talk about particle systems, inside of this video right now. And, I will explain how to do a particle system. First, what is a particle system? Specifically in Unity. It is just a particle system is kind of like a game object that is mainly used for visual effects. So generally you can do like smoke, rain, all this stuff. So there's a lot. It's a very dynamic and unique component of a game object that basically shoots out particles to represent something. So say in I don't even know, Call of Duty, when you run and and it's raining, that's more than likely a particle system. If you go to any game and there's fog, it's more than likely a particle system. If there's smoke, it's a particle system. So overall, it's just a very powerful tool that allows you kind of do a lot of this stuff. We won't go in depth with Unity, but if you look at the component, there's a lot of variables in a Unity-based particle system that I did briefly explore inside of a previous video, but yeah, but we're gonna try and tackle that today. And what I have right now is I just have a particle system example game object that I have. So we got this, and these are some of the variables that I'm going to explain about inside of this course. Like starting particles, particle velocity, lifetime size, color, direction, gravity, particle count, or maintain particle count, continuous particle spawning, continuous spawn intervals, and continuous spawn particle count. Some of these variables are kind of custom and are not in Unity, but there are replacements, or they're just not having the same naming convention. In order to understand particles, though, we first have to understand distribution systems. Within Unity, when doing particles, there is we need to be able to randomize, or at least have the option to randomize the particle count, because you don't always want the same particle to shoot in the same direction every single time. So what we're going to do is there's going to be two distributions we're going to talk about, constant and uniform. And what we're going to do is whenever we need to get that that value for a particle, we're going to sample that particle in order to actually get a value. For constant particle systems, it will just be a constant value, but for uniform, it will be a uniform distribution between two ranges of numbers. So kind of just big picture, what kind of stuff would we want inside of a particle? Inside of a particle? Well, obviously there's going to be a position, and that position needs to be located at 0, 0 relative to the game object it is established. We also want some sort of velocity. Direction, we want to randomize the direction, but we will eventually have control over it. But let's say the direction is all 360. Lifetime, size, start alpha, and in this case, alpha is the variable of opacity. So sometimes, like for fog, for example, you don't want a full opacity particle system because that means that there will not be, you couldn't see through it. So these are just some general variables that we would want inside of this. Now let's look at some samples. So when we do a constant sample distribution, it is just a single value. So for a constructor, here would just be a simple, we will take a value and we will say this dot value equals value. And then when we call a sample function, or whenever we access that sample function, we will return this dot value. So with this, now if we go over here, do we have a yes? Oh, that's a constant. Okay, particle gravity. We want all particles in this case to have a constant distribution of 0. For continuous spawn particle count, that means that we will always spawn 5 particles at a specific time interval, at a random time interval. But in this case, since we're doing a constant distribution, it will always be 5 particles. Now let's look for uniform constructor. This time we will have 2 inputs, a low and a high. And we will say this dot low equals low, this dot high equals high. And what we do is then when we sample it, what we have to do is we have to return math.random times this dot high minus this dot low. So we first get the range of what we can get, and then we add it to this dot low. So just kind of big picture, what it is we get a randomized value between the range of the 2 numbers, and then we add the this dot low to it to raise it, the floor to the correct one. Okay, and now I won't do constant color yet because we will not get to that just yet. Do I need to do... I'm just going to revert that one change to make sure that there isn't an error there. Okay, now for every particle class, we will also need to be able to adjust those variables. So we're going to do a constructor, and we will do the params variable, and we will do the object.assign, which to remind everyone, that object.assign takes in an array of values, or is it an array? It will take all these values, and if they're the same name, so for example, if we override the position value and we have a new position variable in the params, we will assign that params or that new position value to our position. Same for live time and all this other stuff. Then what we want is we will then say this dot start time So now we're going to establish a start time, and this will just equal time.time, whatever time we start at. And now we need to do some velocity. So with this, what we will do is we will say this dot Vx, our velocity in the x direction, will equal this dot direction times math dot cosine this, oh, sorry, apologies, this dot velocity times math dot cosine this dot direction. And then same for Vy, it is this, but instead of cosine, it's sine. So with our Vx, we have our velocity, which is given in here, and we, in order to make it standardized, we will use math dot cosine to get in the x direction, and math dot sine to get in the y direction. And now inside of update, we need to update the position, but first we have to apply gravity, which means this dot Vy plus equals this dot gravity. Now we have to move the particle based on our Vx, and we also need to move the particle based on our Vy. And now we need to account for lifetime. So now we will do if this dot start time plus this dot lifetime is less than time dot time. And again, lifetime is just a variable for how long we want this particle to exist. So if the start time plus the lifetime is less than time dot time, we set this dot is dead equal to true. And we can even have a is dead equals false. It doesn't matter if we have this or not, because what will happen is that no matter what, it would be false because there's no access to it. But we can just even include that as well. And then finally, because we are going to be changing alpha, and alpha is dependent on per particle, we will also get a alpha stat that will, first we'll need to get the percentage of how much has gone. So time dot time minus this dot start time divided by this dot lifetime. So we have the percentage of how much, and then what we do is we return, and then 1 minus percentage. I'll just do percent actually. That's a better variable. And then we do times this dot start alpha. So we see how much remaining alpha we have, and then we plus the percentage of the end, and then by end alpha. So this is kind of how we lerp or transition between the start alpha to the end alpha. Let me just make sure that all of that is good. Yep. Okay. So now we shall do our particle system component. So now this is the actual component that would be added. Since this is a particle system, we obviously need particles equals some array. And now start particles. And now this is where we will use our distributions in order to determine kind of what is what. So what we'll do is for start particles, if a start particles is not given to us, what we'll do is we'll say we will have a constant distribution of 10 starting particles. Our particle velocity will equal a new constant distribution of 1. Our particle lifetime will equal a new constant distribution of 1. And what we'll do is we will sample from these ranges or distributions in order to get for each particle. I think it will be explained a little bit later or make more sense. We'll have our particle color. I will leave that blank for now. Particle direction equals new. This will be a new uniform distribution because we want to assume that you can go anywhere. And with this uniform distribution, we want to start at 0 and we want to loop all the way around the circle of where you can fire. And we will assume that. So what will happen is when we sample this particle direction variable, it will take us, we'll go up to here and we'll say, okay, we're going to return a random value between the high and low plus low. So we'll get a random value between 0 and math.by times 2, and that will be for each particle that exists. And then particle gravity will equal new constant distributions to 0. And then maintain particle count will equal false. Continuous particle spawning equals false. Continuous spawn interval will equal a new constant distribution of 1. And continuous spawn particle count. And these variables will make more sense as we go. And then finally, the last one will be spawn timer equals 0. So now what we'll do is we will do the color distribution now. I think that will be the best. With colors, there isn't a simple, how should I say, there isn't a simple way to do colors, like single variable, like uniform distribution, because every color is made up of 3 values, a red, a green, and a blue. So we have to sample based off of those values. So when we do a constant color distribution, we'll actually have 3 parameters, a red, a green, and a blue, and we will randomize each of those values. And this dot G equals G, this dot B equals B. And what we'll do is when we sample, we will return this, but where it is this dot R, this dot G, and this dot B. So we will always, when we sample, we'll always return this. With the uniform color distribution, we will have to get the range of variables, which means that, so what we'll do is we'll have to have a constructor with a R, a G, and a B, and then a R2, a G2, and a B2. And we can say this dot R equals R, this dot G equals G, this dot B equals B, this dot R2 equals R2. And I'm actually going to do this instead. I'm just going to copy and paste this. And then do a 2. So now we have these variables, and what we'll do is when we sample, we will return some sort of R, some sort of G, and some sort of B. So let's just, one One thing that kind of happens though is that the equation that we used for the percentage for get alpha, where it's 1 minus percent times start, we're going to have to do the same thing where it is 1 minus math.random times it by this dot r plus math.random times it by this dot r2. The issue is though is that when we want to do a random distribution, we want the randomness to first be the same between these two, but also universal between your R, your G, and your B. So we don't want to randomize each value. We don't want to have a distinct random value generated for each R, G, and B. We want it to be universal. So before we do this, what we'll do is we will say a constant rand equals math.random. And now we just reference rand. So now what we do is we do 1 minus random, the random number generated times it by this dot r, plus the random number generated times this dot 2. And what we'll do is we will do the same thing for the rest. Instead of r, it'll be g, and for green, it will be b2. And so this will give us now our a values of r, g, and b between the respective r values, the two r values given, g values given, and b values given. So now, when we do constant color distribution, and I say 255, 255, 255, it will be all white with the constant color distribution. And if we want to change it, then we can go and change it. Like in, did I change it in this? Nope, this was all black. But if I wanted to change it, I can change it by using a uniform distribution. Okay, so now for start, what we'll do is we will say this dot start particle count and it will equal this dot start particles dot sample. So now we have sampled the start particle count, and we will so now given whatever random distribution we have, now we have a starting particles that we will need to draw and update. Now what we'll do is we will just do this dot draw particles, and we will add this dot start particle count to it. And draw particles will obviously just be the logic for drawing stuff. And then finally what we'll do is we'll have this dot current interval equals the continuous spawn interval dot sample. So now with the current interval, if we do continuous spawn, if we do continuous particle spawning, we'll just have that variable reference for future. Now, I think draw particle is probably the easiest. So with draw particle, it's not really drawing the particle per se, it's more instantiating the particle like how we instantiate a game object, for example. So what we'll do is we'll have to loop through our particle amount. And then I plus plus. And what we'll do is we'll do this dot particles dot push. And this is where we can actually input our variables at. So say we want a velocity to change. This is where we can adjust all of these variables. So say we want to start at a different position, we can have position and then start at vector 10, 10, for example. But the thing that we can also do is what we can do is actually do this dot particle velocity dot sample. And what this will do is we'll say, let's assume that it's a uniform distribution of 1 and 10. And I'll change it back for, but what this can do now is when we create a particle system and we want 10 particles, I'll put the starting particles of a new constant distribution. And what will happen is when I draw my particles, I will sample this particle velocity range 10 times, each one giving its own unique value, or each particle getting its own unique velocity value, and it will be pushed into this particles, which will then be drawn and updated. So what this means, overall big picture, is that now we have a system where each individual particle can get its own unique values based on a range given by the particle system. And we can do this the same thing for lifetime. Is lifetime. Yep. So we can do lifetime is the this dot lifetime. Particle lifetime dot sample. And let's change this back. But yeah, so now we can do variables like lifetime, size, color, direction, gravity. And now all we need to do is reference the corresponding distribution system. So for size, we do this dot particle size. Oh, did I forget particle size? I might have forgotten particle size. Yep, I did. So now we have particle size. So now when we reference the particle size, we can just sample the particle size distribution and therefore have a unique particle size for all of them. Same for particle color, dot sample. This dot particle direction dot sample. And this dot particle gravity dot sample. So when we draw the particles, we just instantiate all of the particles into this particles array that we have in the beginning. And each one will be, each one of its characteristics will be sampled from the distribution. And now for draw. This is slightly different from how we do other draw functions. So I think this will be constant particles of this dot particles. This would be slightly different from how we draw other game objects and stuff like that, because what we do is when we do CTX dot fill style, we have RGB values, and we also have an opacity value now. So there's a little bit of a difference now between how we get it. Luckily, JavaScript accepts this RGBA logic. And what you can do is if you do $, and then curly brackets, you can actually do something called string formatting. And what we can do is we can do this 4 times to get our RGB in a value. So now instead of doing red ctx.fill style equals red, what we can do is we can actually get the color now. So we can do particle.color.r for red, .green or .g for green, and .b for blue. And then what we can do is then we can do particle.getAlpha for that alpha value at the end. And then what we do then is now we just do ctx.beginPath. Okay. If you remember early on, we talked about how we can draw a circle easily with ctx_arc. So that's what we will do. And this will just be a particle.position.x plus this.transform.position.x. So what we do is we get the local particle position and we add it to the particle component position. Same thing for the y value. Our size will just be particle.size. And we'll go from 0 to math.pi times 2. And we'll do ctx.fill. Finally is update. There is there's some logic in here. So what we'll do, that is a little confusing or very specific. So I will try and do this as best as possible. But what we'll do is spawn timer. Okay, first we need to update our spawn timer variable. Our spawn timer variable will establish how much time has passed between starting this particle or this particle system starting. What we'll then do is we'll now loop through our particle, and it will be, we will just call particle.update, which will update the velocity, the position, and that stuff for every single particle. And then finally, we got to do is this dot particle equals this dot particles dot filter. And what we do is for every particle, let's just do P, we say we filter it based off not this dot is dead, or P dot is dead. And now hopefully, let's see. So for constant, let's see. Does particle have a value? Huh. Let us check this out. So that doesn't matter. Is there any difference in here? I'm trying to see if there's any logic I'm missing. Oh, yes, I am. That is where I am wrong. In here, it needs to be a new particle with this right there and that right there, and we control Command F to format it. See, and now we have a particle system with what we have, and you see how every single particle has its own unique velocity, direction, and we can even go through. I think now is a good time to go through this particle example component. So now what we have is we'll have a particle system whenever I reload the page that will have a distribution between 10 to 20 start particles. The particle velocity will be between 5 and 10. The lifetime will be from 0.25 to 1. The size will be from 1 to 2.5. Particle color will always be black. The direction will always be from math.pi to math.pi times 2. So that's why you see no distribution on the lower end of the particles. We have a particle gravity of 0. So if instead we change that to 10, for example, you see how it instantly goes, let's do 1. And you see now how it's more like I don't even know what that would be. But it's now pulling downwards. So say we want to even lessen that. You could almost make it look like a firework if you add multiple particle systems on top of each other. But yeah, but right now we have 0. And then we haven't done this yet because this logic is a little bit more complicated, which we will start doing now. But say we wanted to change particle color. What you could do is you could do uniform color distribution from 0, 0, 0 to 255, 255, 255. And now when we reload it, it's hard to tell. So let's go like red. And let's make sure that the lifetime is between that and let's do like 2. Let's increase the size to like 5 to 10. So we can really see the colors. And you see how all the colors are now slightly different? But instead of reloading the page, I want to continuously spawn particles. So that's what we shall work on. Since this is big picture managing particles, we're going to update the particle system update. And what we will do is, what we want to do now is we want to get the difference between what we currently have, which is the start particles count, minus what we currently have, which is this dot particles dot length. So now we get how many particles are dead or have despawned. And then we do a simple if value where if this dot if we want to maintain particle count and the particle count difference is greater than 0, we now need to reinstantiate the particle system. So what we do now is we do this dot draw particle count difference. Technically, you don't need this particle count difference is greater than 0, because if it's 0 particles you're adding, that means that it will just be that I equals 0, I less than 0. But why even make that call to begin with if we don't need to update it? So now what should happen is now it's continuously spawning our initial value of particles. So say you are doing a smoke or something and you want it to be a mixture between, so now let's try and make a smoke kind of area. So let's do 100 to 200 particles. Particle velocity will decrease to like 1 to 5. We want gray values. So I'd be fine with 0 to 255. I'm fine with the lifetime. We want to decrease the size to like 0.25 to 0.5. We want a very, very slight kind of gravity, so like maybe like 0.1. It is still... Let's increase particle size to make sure it's still working. Let's do 2 to 5. Yeah, to be fair, I don't know if we can do smoke actually, now that I think about it, with this system. But yeah, hopefully this is a very expansive system enough to do stuff, to do more creative stuff and think outside of the box, specifically with maintain particle count. But now we have to do a little bit more logic where if now we have to, instead of doing maintaining particle count, I want to do continuous particle spawning interval. So we need to do a little bit of logic where if this dot continuous spawn interval, and what continuous spawn interval will do is it will, continuous spawn particle. And what this variable will do is, if it's true, we will always spawn a particle, do a spawn particle at this time. And then what we will do is, then we'll say if this dot spawn timer is greater than this dot current interval, and this dot current interval is greater than 0. So if we're past our current interval time, and our current interval time is greater than, and exists, so it should be greater than or equal to. What we'll do is now we will sample then, or not sample, we will do draw particle, and the map we'll do is the continuous particle spawn count dot sample. So what we'll do is we will sample this distribution for how many times we need to spawn this new particle, and then what we do then is then we reset this dot spawn timer equal to 0 to then reset when we need to respawn the interval again, and then we set this dot current interval. And now what we want to do is we want to get the new continuous spawn interval sample for our system. So now what we'll do is, to test this, I'll have 1 to 2 particles, but our continuous spawn interval will be 100. So we can actually see if that works. And now it's more of a burstiness. And in order to actually to show that even further, let's go from 0.5 to 1. So now between 0.5 seconds and 1 second, we will burst at a random time. And if we want to increase that further to really exasperate it, Sometimes it'll be 0.5, sometimes it'll be closer to 2, but it is that randomness now that we can kind of burst those particles. So say, for example, one way you can use this is, say you have a, like in a real, or an example of when you would do this is a fuse box. Say you have a broken fuse box in a game and you want to show it's broken. What you can do is you can use white particles and you can do these like bunch spawning for like the electricity sparking off of it, for example, that type of stuff. If so, like there's a lot. Hopefully, there is a lot of creativity you can do with this particle spawning, with some of this. With some of this stuff, because this is probably one of the more powerful tools outside of game object hierarchies that Unity provides and that we're going to cover. And yeah, I hope that this kind of explains a lot of it, to the point where you can understand it, and that when you go into Unity, you kind of understand some of the particle system variables, because again, when we actually look at Unity's particle system, it's very powerful, but there's a lot of variables that can have. There's a lot of variables that we haven't discussed. So like if we go to the API, there's so many. So there are some properties like collision that I've worked with. You can pause particle systems or play them or stop them. There's a way to make them have lighting. There's particle count that we've done. You can do it by seeds. You can rotate the particle system. Yeah, there is a lot. And then here's way more. So there is a size by speed. So what you can do is you can align the value of the size by the speed. So say you want bigger particles to move slower, that type of thing. You can do emission stuff. So you can have some emissions. You can do colliders, color by speed. Yeah, there is a lot. So hopefully, though, that kind of helps you understand particle systems so that you can kind of get another avenue of exploring stuff. Hope you have a good one.